Okay, I think it's time to start the next session. We're going to keep it in the PSI family for the next two talks. The first one will be from Jaspal Singh. He'll be talking about his work on distance-aware OT and applications to Fuzzy PSI. Go ahead, Jaspal.
Thanks for the introduction. So I'll be presenting one of our recent works on fuzzy private set intersection. This is a joint work with Lucas, Nee, Vlad, and Vasilis. By now, I assume you all are familiar with the standard functionality of private set intersection, which allows Alice and Bob, where one of them to receive the intersection of these sets privately. So throughout this talk, Alice will be the receiver of PSI, and Bob will be the sender. And traditional PSI has been well studied for the last 2 decades, and we have as Nee pointed out, a lot of research in this direction, and it has been heavily optimized. My focus today will be on a variant of private set intersection, particularly fuzzy private set intersection. So in a lot of applications, you deal with data that is imprecise or measurement-based. So in that case, if you want to use private set intersection, often you would prefer some sort of a fuzzy match instead of an exact match. Or formally, you would want Alice to learn points of Bob, which are within some threshold distance delta of its own points, where this distance metric could be defined based on your applications. Another very natural definition you could have come up with on your own is where Alice essentially learns its own points, which are within delta distance of the sender. This is called the sender private definition of PSI, fuzzy PSI. But for this talk, I would be focusing on the former definition, although there are works which focus on the latter. So there are a number of works which have used fuzzy PSI directly or indirectly. Just to note some of them, it's essentially used in checking for compromised passwords. In practice, we often tend to use similar passwords. So essentially, you could use a fuzzy PSI protocol to check if a similar password has been compromised in a public database. Another application is for biometric authentication. Here again, you need some sort of a Hamming fuzzy match between a larger data set and your own biometric data. Those were more so on the unbalanced setting case, where you have a large set and a smaller set. But you can also envision a fuzzy match where you have 2 large data sets. So one such example is where you want to do fuzzy join of 2 large databases, and you want to do some further computation on that. In general, you can think of any PSI application where you deal with measurement-based data sets or noisy data sets. And there, essentially, a more apt tool might be fuzzy PSI instead of traditional PSI. So there's been a long line of work on fuzzy PSI. Specifically, recent works on fuzzy PSI can be broadly categorized into 3 domains. One where the fuzzy matching is done using function secret sharing. One where public key assumptions are used, DDH or homomorphic encryption scheme. And there's also recent work based on garbled circuits. Unfortunately, although all of these approaches have some advantages over the other, they all essentially have really poor computation, really poor complexity, especially if you compare it to traditional PSI. So even for 2 to the 16 elements, whereas traditional PSI would take 1 to 2 minutes, even the most efficient fuzzy PSI would traditionally take 10 minutes. And that too is in the very limited case where you have just 2 dimensions and you're doing some sort of match in Euclidean norm or even Manhattan norm. So essentially, there is this large gap between PSI and fuzzy PSI concrete complexity. And in our current work, our goal was to try to bridge this gap. And specifically, our focus was to design a symmetric key-based framework inspired by the most efficient PSI schemes, which are based on OT and Vol extension. So we essentially build a modular framework based on oblivious transfer. And at the heart of our construction is a new primitive which we call distance-aware OT, which essentially is used to build our Fuzzy PSI framework. Throughout the talks, I'll focus just on the LP norm, although a lot of the ideas could be extended to other norms as well. But for this talk, we wouldn't talk about eddy distance or Hamming distance. And also, I'll stick to semi-honest security. So going back to the efficiency scale, so for the same parameters that I mentioned earlier, so our work will get you to 30 seconds in 2 dimensions. For higher dimensions, it still doesn't scale well. And you might say 30 seconds is still pretty far away from the 1 second of PSI. So I will say we bridge it qualitatively. So we just have an OT-based scheme, and hopefully this can be optimized further. So looking back at a framework, it is essentially built in 3 stages. You have distance-aware OT, which you will see it as a single fuzzy match. And at the end, you have fuzzy matching, where our goal is to do batch fuzzy matching between 2 large sets of Alice and Bob. And I'll have an intermediate building block, which will sort of help us go from this single matching to batch matching, which I'll term sparse matching. So we'll build it in this approach we'll go from essentially top to bottom. And another thing to note, distance-aware OT will build it for small domain, but somehow we'll be able to extend it to fuzzy matching, where we're dealing with arbitrarily large domains. So what's distance-aware OT? Essentially, you have Alice and Bob, a receiver and sender, which input 2 keywords from some domain. And similar to oblivious transfer, the sender receives 2 random messages, and the receiver receives one of those messages, where the selection bit C is defined based on the distance between the input keywords A and B. So if they are within some defined distance delta in your distance metric D, then essentially Alice would end up with the random message R0. I will note that a similar definition did arise in another work around 20 years ago, but they were focused on just interval comparisons, whereas ours is focused on arbitrary distance metric. So the key building block for a distance-aware OT will essentially be a 1 out of T OT, where the sender inputs a vector of messages, specifically T messages. The receiver inputs an index from 0 to T minus 1, and it receives as output the Cth message, where C was the input. And specifically for a clean representation, we will essentially use a variant of that OT, which we'll call shared oblivious transfer. Here, essentially, the choice bit is secret shared between the sender and receiver, and also the output message of the OT is secret shared. You can essentially get this from traditional OT by doing some sort of corrections, but for a cleaner presentation, we will use this primitive. And in fact, to reduce clutter, I'll use this simpler notation, where the choice bit is secret shared and the output is secret shared. So going back to a distance-aware OT, how do you construct it from these oblivious transfers? So I'll essentially give 2 examples, one based on Chebyshev norm. Chebyshev norm is where you take the maximum distance along each dimension between the two input points. So you can, in 2 dimensions, essentially an L infinity ball turns out to be a square. So this is an L infinity ball centered at B, and to check if A is within distance delta, you are essentially checking if A is present in this square. And another example is Manhattan norm, which is also the L1 norm. And here our goal is to check whether the sum of the distances sum of the projections of the points along each axis is bounded by delta, which in 2 dimensions turned out to be this diamond shape, and for higher dimensions, it has a more complex geometry. So let's begin by Chebyshev norm, which is the easiest to deal with. And essentially, we're going to use our shared OT primitive to build this up. And again, I note that we are working with small domains. So essentially, the sender prepares this vector of message, which is a bit vector of size u, which is u is the size of the domain, and it's 1 exactly in the interval of your square, the square that I showed earlier on the left side. And essentially, Alice gives AI, which is its projection, which is essentially its coordinate in the ith dimension as its choice bit. And they end up with secret shares of hi. And hi is essentially an indicator bit telling whether AI is present in this interval or not. You can do this for each dimension, and you can sum it up. Now you can think of what h represents here. Specifically, h will be equal to delta if and only if the distance between A and B is at max delta. Right? If h is lesser than delta, it essentially means the point A wasn't in the ball centered at B along some dimension. So essentially, we invoke an SOT again, where the sender samples some randomness from some domain, and this is input, and this is used to prepare this vector of length delta plus 1, corresponding to all possible values of h. And essentially, it has r in all coordinates except the last coordinate where it's 0. And this h is fed into the SOT as the choice bit. Now note, the output of this SOT can be used to construct your output of distance-aware OT, where the output share of the receiver corresponds to the received message, and the share of y that the sender gets, you can essentially have an additive share of r added to the second message to get both the messages. It's easy to verify that this satisfies the given definition. So if the distance between A and B was less than delta, essentially the shares would add up to 0 of y by construction. Or in another case, m prime would be exactly m0, which is what we want. And in the other case, m prime would end up being m1 because of the r, additive factor of r. So essentially, that gives us a distance-aware OT for small domain for Chebyshev norm, where we invoke nothing but just a constant number of SOTs without no other interaction between Alice and Bob. So given the time, okay, so I'll quickly go over Manhattan norm as well. So in this case, this is a little different because instead of max, you end up with the sum. So essentially, you can think of this distance as us having some budget of delta, which you can spend along each dimension. So essentially, Bob prepares this vector zi, which essentially computes how much of the budget Alice can spend based on its input in the ith dimension. So I wouldn't get into the details of the math, but essentially hi captures how much of the distance, how much is the distance between ai and bi, how much is the absolute distance between them essentially. And when you sum it up along all dimensions, you want this sum to be less than or equal to delta. Only then would A be within distance B, within delta distance of B. And essentially, that's what's captured there. And now, similar to the previous approach, you sample some randomness. You prepare a vector for all possible values of h, with 0 corresponding to the values of h where A and B have distance less than delta. And the same math follows, and essentially they end up with a distance-aware OT for the Manhattan norm. So the same logic sort of follows for Euclidean norm as well, but unfortunately it only follows for dimension 2, and maybe you can give it a try to try to extend this argument for higher dimensions. So we're done with the first primitive. So we have these really nice distance-aware OTs, which you can build from nothing but classic OTs. And now I'll define the second primitive, which is sparse matching. So sparse matching essentially corresponds to multiple instances of fuzzy matching, fuzzy matching, where essentially each fuzzy matching has a corresponding index by each party. So Alice inputs, in this case, 3 fuzzy inputs, fuzzy matching inputs, x1, x3, and x6, and it has a corresponding index 1, 3, and 6. Similarly, Bob inputs 4 fuzzy matching inputs with corresponding indexes. And what we want the sparse matching functionality to do is essentially to output a pair of messages for each index to Bob and a single message to Alice, such that whenever an index is common across their 2 inputs, essentially the output should be consistent with the output of daOT corresponding to the input keywords. And whenever you have an index in Alice or Bob's set, which the other party doesn't have, the corresponding R values should be random. So note that just by this primitive, Alice does not learn anything about the indexes of Bob. Similarly, vice versa as well. So to construct such a sparse matching protocol, we essentially make a key observation about a distance-aware OT, that essentially it invokes nothing but a constant number of OT, essentially each of our distance-aware OTs, and there is no other interaction. So we term those as zero-round SOT hybrid protocols, and we note that all the DA distance-aware OT that we design sort of follow this framework. And then we have this sort of really nice theorem, which essentially says, if you give me a daOT protocol in this SOT hybrid, zero-round SOT hybrid model, then essentially I can give you a sparse matching protocol for the same domain and distance metric in a sparse SOT hybrid model, which is a variant of the SOT model, SOT functionality. So just to define sparse SOT, it's defined naturally similar to sparse matching, where parties essentially have multiple instances of SOT, each labeled with an index. And here again, the outputs of this functionality would be consistent if they have a common index. And in other cases, you end up with random shares. I wouldn't delve into how to construct these sparse SOTs, but it follows from another similar sort of work based on sparse OT from 2019. And it's essentially, you can think of it as an OT extension. So going back to our main theorem, to put it in other words, if you have a matching protocol that's in the OT hybrid model, you end up with a sparse matching protocol that's in the OT extension hybrid model, essentially, or a batch OT hybrid model. Again, this I wouldn't present this construction in detail given the lack of time, but it's a very natural construction, which you can. It's the most sort of obvious construction that you can think of, given that the parties have no interaction other than just calling these SOT primitives. So now we come to the last step, which is essentially how do we do fuzzy matching, given that we have developed this sparse matching. So far we have only worked in this small domain, and now we'll be working over an arbitrarily large domain. So let's take a simpler example. Alice has 4 input points labeled colored blue in this case, and Bob has 3 input points. And let's say we pick some delta and LP norm such that x1, y1 and x3, y3 are within distance delta. So the first step to our Fuzzy PSI protocol is to do what is called spatial hashing, which is just a fancy word for sort of very basic sort of level of hashing. So essentially what Alice does with its points is to essentially it I've skipped a step. So first of all, you construct a grid structure over the input domain, where the side length of each cell is 2 delta, where delta is your threshold distance. And now essentially Alice hashes each of its points to the corresponding cells that contain it. And what Bob does is Bob hashes each of its points to the entire neighborhood of that cell. So Y1 essentially in this case would be hashed to all the neighboring cells as well. And this is also called the neighborhood of a cell. Similarly, you do it for Y2 and Y3 and you end up with this. Specifically note that some cells will have more than a single entry of Bob, and that is what we'll define as the neighborhood of the center, the density neighborhood of the center set. So that's signified by rho. In this example, it is 2. So our protocol would also leak this parameter rho, and of course you can upper bound that if that is a sensitive parameter. So going back to a question of how do you check if the distance between any point of Alice and Bob is within some distance delta, essentially needs to meet 2 criteria. First of all, xi and yj needs to be neighboring. That is, they need to be in the same cell or adjacent cells. And secondly, if you truncate x and y to just their log 4 delta bits, essentially their distance would be less than or equal to delta. And that sort of intuitively makes sense, because if some points are in the neighboring cells, to compute their distance you can remove their high order bits and just compute the least significant bits given the size of the cells. So essentially we need to satisfy these, to check distance between points xi and xj, you need to satisfy these 2 criteria. Now given our spatial hashing, we'll essentially compare each point of Alice to points of Bob which are hashed to the same cell. And to do that, essentially we'll use our sparse matching. Another key point to note is that we reduced fuzzy matching over a large arbitrary domain to now trying to do fuzzy matching over these truncated values. So essentially Alice prepares this dictionary where essentially all the key values corresponds to the cell. So essentially I've labeled these cells as C1, C2, C3, C4 that contains these points. And for each cell, Alice will essentially add 2 entries to its dictionary, indicating the fact that each element of Alice might be compared twice with an element of Bob, given the density is 2. So that's why x1 is added as a value twice with 2 different key values for the dictionary, and the same for x2, x3, and x4. And similarly, Bob is going to hash its own points, prepare its own dictionary with a similar coordinate system for the cells. And now essentially we can invoke the sparse matching functionality. And by definition, since only x1 and y1 and x3 and y3 are within some distance delta, what you get as output of sparse matching will all be random strings except for those specific coordinates. So only in those cases will you end up with matching strings for the sender and receiver, which are indicated by green and yellow, whereas in other cases you'll end up with random independent strings. Now to conclude the protocol, we just want Alice to learn points of Bob corresponding to these green and yellow labeled keys. So the natural idea is you can encrypt essentially these values y2, essentially y2, y1, and y3 using the corresponding keys that were output by sparse matching. So essentially use the outputs of sparse matching as keys for encryption, and you essentially send that to Bob. Alice. And Alice essentially uses its outputs of sparse matching, and it treats it as keys, and it tries to decrypt all the ciphertexts which it received from Bob. And now, of course, by our definition, it wouldn't succeed in decrypting any of the ciphertexts except for the green and the yellow one, And the decryptions essentially give you the fuzzy intersection, y1, y3. This is not very concretely efficient because Alice will have to try each of its key with each of its ciphertexts. So to make that sort of more optimal, you can use an OKVS, which essentially has two functions, encode, decode, and it satisfies three properties, which will be critical for our protocol. Essentially, it satisfies some sort of correctness. If you look at any encoded dictionary using this OKVS, and you try to decode it at any x that was in the dictionary, then you end up with the expected output. It has a very efficient decoding. So if you query this encoded dictionary, you can retrieve the output in constant time with respect to the size of the dictionary. And finally, you have this really neat property of obliviousness, which says that no matter which set of keys were used to prepare your dictionary, as long as your values were random, the adversary won't be able to distinguish between these two encodings, which is essentially the two encodings corresponding to the two set of keys. So to sort of go back to our protocol, instead of just sending all the ciphertexts, you can send an OKVS encoding of all the ciphertexts with the corresponding key values are the key values of the sparse matching. And Alice can essentially use the same key values to try to decode the OKVS and then perform decryption to learn the fuzzy intersection. So to conclude, so we give this sort of symmetric key-based approach to Fuzzy PSI, where we reduced batch fuzzy matching to single fuzzy matching, which is reduced to oblivious transfer. And secondly, as I note that there is this implicit leakage of size of the sets and also the neighborhood density of the points of the sender's set. And finally, while I only discussed Fuzzy PSI, you can sort of naturally extend this framework to do other related functionalities, including fuzzy cardinality and fuzzy inner join. And I'll conclude on some open problems in the domain of Fuzzy PSI. So there isn't a very concretely efficient way to do malicious Fuzzy PSI. And while ours is concretely efficient for some small dimensions, you see an exponential dependence on the dimension parameter. So maybe it might be interesting to explore some other data structures which might help perform, better for higher dimensions, which are also sort of fit well with our OT model. And again, our distance-aware OTs were only for some limited distance metric, but you can consider designing them for any metric, any sort of distance metric, and sort of the framework generalizes for that as well. And finally, I'll mention that this sort of notion of sparse secure computation is pretty interesting. This was also noted in the context of oblivious transfer earlier, and in our case, we notice it in terms of fuzzy matching. So I think it might be interesting to see if there are other applications or protocols where you want to do this notion of sparse MPC, where you want the correct outputs whenever the indexes match. Thank you.
Questions?
Yes.
So can you go back to your conclusion slide? I'm gonna make a claim. I'd like you to sort of show where this is wrong. Mm-hmm. So if you just use garbled circuits for your daOT primitive, you would also use OT. You'd use fewer of them because you would use OT extension, and then it would also only be based on symmetric key and OT. And then you'd answer all of the other questions. You could naturally extend it to malicious. You could get better complexity because I think you use fewer OTs. So if not my particular construction, you can imagine a construction in a garbled circuits model. Why doesn't that meet your criteria?
So actually, there's a parallel work by Mike and his team as well, where they actually use a very similar framework where they do matching based on garbled circuits. So sort of a similar framework does extend. But I will note that there is a challenge for malicious, specifically when you talk about this sort
yeah,
of
so maybe one of your reduction steps, like the encoding reduction steps. But let's say we do the whole thing with garbled circuits, like what complexity measure gets blown out by that? Like, I don't see in your construction or reduction where you're using the data structure or where some sort of aspect of the problem is beating the garbled circuits check.
So yeah, essentially, I think there are, if you use naively, where you match every element of Alice with every element of Bob, you end up with quadratic costs, right? So that we start sort of outperforming that at very small inputs. That's something we have verified. And even for distance aware OT, now note that we just use a constant number of small number of OTs to do the fuzzy matching. Garbled circuits would have an higher concrete overhead, but maybe that's something to try as well. Yeah. Any other questions?
Okay, let's thank Jaspal again.
Relevant thing.